In this video, we start off with a 2x2 matrix, which we call A. And it says that A is row equivalent to I2, the 2x2 identity matrix, if and only if AD minus BC is not 0. So let us prove this. So we're going to start off with A is row equivalent to I2. But that implies A and C can't both be 0. Else, A will equal to 0B, 0D, which is not row equivalent to I2, since A has a column of zeros. So suppose that at most one of A and C are 0. And then we break this down, say, to two cases where one of them is 0 and none are 0. Suppose only one of A and C are 0. If A equals 0, then matrix A is equal to 0B, CD, which is row equivalent to CD 0B. And C is not 0. Hence, without loss of generality, assume A is not 0. Better yet, assume C is 0. Okay? There's only one of them in case 1 is 0. Okay. So A is equal to A, B, 0, D. And to row reduce this, I would like to get the B to become 0. So we're going to change row 1. I'm going to multiply row 1 by D, and I'm going to multiply row 2 by B, and I'm going to subtract. So the second row did not change. Okay, so let's do the side work on the side. D times row 1 is AD, BD. And B times row 2 is 0 times B, and B times D. And if I happen to subtract, the new row 1 will be AD 0. AD 0. Okay. Now, D is not 0, else A is equal to AD 0, 0, 0, which is not row equivalent to I2. So D is not 0. Okay. So A is row equivalent to AD 0, 0, D, and D is not 0. Now to get the identity, I will divide row 1 by AD, and I would divide row 2 by D, and what I will get is 1, 0, 0, 1, which does equal to I2. Okay, so now AD minus BC. Now, A is not 0. D is not 0. But C is 0. A was not 0. D was not 0. And C is 0. So this is 0. So you have AD, and a product of non-zero numbers is not 0, minus 0. That's not 0. Okay? AD minus BC is not 0. So that case is okay. Now case 2. Case 2. A is not 0. Oops. Not 0. And C is not 0. So A is equal to AB, CD. A and C are not 0. So I want to get C to be 0. I want to row reduce it. So I'm going to take row 2 and multiply it by A. And I'm going to take row 1 and multiply it by D and subtract. First row, we didn't do anything to. Now, 8 times row 2 will be 8 times C, 8 times D. And D times row 1, that will be AD and BD. Okay, how about we multiply row 1 by C, excuse me. How about we multiply row 1 by C. It was a big mistake. And I get AC, BC. And then if I happen to subtract, I get that the new row 2 is 0, AD minus BC. So I get 0, AD minus BC. Now, the only way, if this is row equivalent to I2, that implies that AD minus BC cannot be 0. Which is what we wanted to show. But let's be careful that that doesn't get contradicted in a moment. So what I can do is say that A is row equivalent to what I already have, AD minus BC, and then I'll divide row 2 by AD minus BC, and this gives us AB 0, 1. And then I can knock off the B. I can take row 1 and just subtract off B times row 2. That's going to give me A0, 0, 1. And then if I divide row 1 by A, and somewhere we said A is not 0. In fact, we said A and C are not 0. So what I get is that I have 1, 0, 0, 1, which is row equivalent to I2. And the only restriction was that AD minus BC is not equal to 0. For example, if I also got that AD plus, I don't know, BA has to be 0 or not equal to 0, then that's a new constraint. And the theorem wouldn't have been proven. But we only had this constraint, which is good. So in one direction, we're done. Now we need to go in the other direction. We must show that AD minus BC not equal to 0 imply that A is row equivalent to A2. Now we know that A is equal to AB, CD. Now, we also know this. A A is not, well, let me say it correctly. A and B can't be both 0, else AD minus BC, which is 0 times D because A is 0, minus or B times 0 because C is 0, which is equal to 0 minus 0, which is 0, and we're saying that it's not. Okay. Likewise, B and D can't both be 0. In fact, you cannot have one of these two being 0 and one of these two being 0. In other words, you can't have A and B being 0, because then the subtraction will not be not 0. You can't have A and C both equaling 0. You can have D and B both equaling 0. You can have D and C both equaling 0. Okay. So what we know is A and C can equal 0, and B and D can equal 0. That is, you can't have a column of zeros, and you can have any row being 0. Okay? All right. So let's write this out. So, no row nor column of A can be made up of just zeros, else AD minus BC will equal to 0. Okay, so let us see how this is going to play out. So we want to reduce A, and A and C can't both be 0. A and C. Just like before, we can interchange the two. In case it's the A that is 0, I can interchange the two rows, and C will be in the 1, 1 position and not be equaling to 0. So without loss of generality, assume A is not 0. Now, A is A, B, C, D. If I want to get the C to be 0, Even if it already is 0, it'll stay 0 under this multiplication. If I take row 2 and multiply it by A, which is not 0, and I take row 1 and I multiply it by C, where C may or may not be 0, I'm clearly not changing row 1, and A times row 2 will be AC, AD, and C times row 1 will be AC, BC, and if I subtract, I get new row 2, which is 0, AD minus BC, which we know is not 0. So I get 0, AD minus BC. Now, in case C was 0, in case C was 0, I mean, A times row 2, if C was 0, would have been 0 AD, and C times row 1 would have been AC, BC, and if I subtract, remember, if C was 0, this would be 0. So I still get the same row. I still get the same row. Okay? If C were 0, I still have the same row 1, and all I did was multiply D by a non-zero value. Now, just for the record, if C is 0, D can't be 0, because AD minus BC, if C is 0, that product is 0, and if D is 0, that product is 0, we get 0. Okay. So now, if I take row 2 and I divide it by this non-zero value, I will get AB01. And then if I do row 1 minus B times row 2, A minus B times 0 is still A. B minus 1 times B is B minus B, which is 0, 0, 1. A is not 0, so we can divide by A, and we get that matrix A, which equals this matrix, which is row equivalent to 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 that last matrix, which is 1, 0, 0, 1, which is not row equivalent. I guess it is, but it equals I2. That is, matrix A is row equivalent to I2, just in case AD minus BC is not equal to 0. And maybe over here we should mention that D is not 0 if C is 0, because else AD minus BC will be 0. And let us put the C back here. Okay, because if C is 0, we just get AD. But if D is 0, then we got 0, which is a contradiction. There's the proof. It had a lot of twists and turns in it, but there's a valid proof. If you know of a better proof, submit it. I'd love to see it. If you love to see proofs like this, subscribe to my channel. Leave a comment saying how much you hate or like my videos. But as always, watch and learn.